Hello again. The last video was getting a little bit long, so I didn't get to the schematic nor the building of the counter, but we'll do that in this video hopefully. Before we get started on the relay logic, there's one thing I have to tell you, because the Nixie tubes have a common high voltage anode, and the 10 cathodes are switched to negative, to ground. I'm using ground as a logic level 1 and either floating or positive 12 volts or floating as a logic level 0. May seem a bit counterintuitive, but it works the easiest for the Nixie tube, so that's why I'm using ground as logic 1. Okay, so let's get the circuit. I found this circuit online at relaybc.sourceforge.net. It's a really nice circuit. I like it because it has a relay count of only 2 relays. I've drawn the circuit with double pole, double throw relays, but it can also be made with single pole double throw relays. But I have all double pole relays lying around, so I'm using them. I just double up on the poles. This circuit works with a sampling relay, storing the sample in this capacitor, and a latching relay. To understand how it works, we need to have a closer look at the latching relay. The latching relay basically has the coil connected in series with a pull-up resistor to the 12 volt power supply. Now the relay, the state of the relay is as it was, like the previous state. So if the relay was off, it will stay off. If the relay was on, it will stay on. And this is done by the 1.5 kilo ohm resistor. The way I calculated this is connecting the relay coil to my bench power supply and ramping up from 0 volts to 12 volts. And I found that it turned on at 6.3 volts and 43 milliamps. Then I reduced the voltage from 12 volts to 0 and found out it switched off at 1.6 volts at 6 milliamps. So the voltage in between these two values means that it will stay either on. If you go above 3.6 and drop to, let's say, 4 volts, it's not going to switch off because it has to go below 1.6. But once it's off and you drive it back up to 4 volts, it's not going to switch on because it hasn't reached 6.3 volts yet. So to calculate this resistor, I basically found the voltage drop across the resistor in the on and the off state, so that's 12 minus 6.3 and 1.6 divided by the current that the coil draws at that time in the on and off state, and I came out with these two values. Now if I choose a resistor below 133 ohms, it will always be on, because I won't be able to pull it low enough. If I go above 1.7 kilo ohms, then it's a very small resistance, so then it's difficult to switch the relay off. So the value of this resistor has to be somewhere in between. I chose a nice high value, still well below the 1.7K, but nice and high value to reduce the amount of current that's always flowing through the relay. So then we have a look at the sampling bit. Right now it's just a switch. I can connect this capacitor to either ground or 12 volts. Let's say the relay is off and we connect the capacitor to ground and we close this switch, then this line will be pulled even further to ground as the capacitor charges. It's not going to charge very much because of this high resistor, but it's not going to turn the relay on because the voltage will be too low. So let's open the switch again and connect the capacitor to 12 volts. Now it's charged up to 12 volts. This time when we close this switch, this current will get dumped into the coil, and this extra amount of current plus the current flowing through the resistor is enough to turn it on. The capacitor will empty. It will still charge through this one to a certain voltage, but the relay will be on and it will stay on even if we open the switch. So in order to turn it off, we connect the capacitor to ground, discharge it completely. Now when we close the switch, it'll actually suck the energy out of the coil and make sure it drops below the 1.6 volts and switch it off. When we open the switch, it will remain off. So I hope that's clear. You can always find a better description on the website where I got it from. So yeah, let's have a look. This is the sampling capacitor. This is the sampling switch, which is my clock input signal. When the clock is floating or high, the relay doesn't do anything. When it's pulled low, the relay is activated, and the capacitor will be connected through this line to this relay here, and this one basically switches between positive and negative. So in the first startup, this relay will be off and will be connected to the plus 12 volt supply rail. This resistor is basically an inrush current limiting resistor to reduce the peak current that the capacitor demands when it's empty. So when we're sampling, when the capacitor is charged up, then when the ground disappears and the input goes floating again, this sample inside the capacitor is then passed through this line to our latch relay with the pull-up resistor. So it'll go on. This switch will come down. And again, next time the clock has a logic 1, which is connected to ground, it will close. And this time the sampling capacitor is connected to ground, so it will discharge through this resistor. And again, when clock goes floating, that 0 volts is connected again to the latching relay, and this time, because it's empty, it will drain the coil and switch off. So I hope you can see that for every pulse you get on the output, it requires 2 pulses on the input. So that's basically a divide by 2 circuit. The next thing I have to do with this is decide how to make all the joints on my little relays. So I start off with a rough sketch. I draw the contacts of the relay and the coil, and I start filling in the components and try to fit everything as neatly as I can around the 2 relays. The relays are spaced very close together, so there's not much space in between. And here you can already see I have the feedback from the output to the input going next to the relays. The LED is actually here, but this resistor is also flowing next to the relays, so that has to be 1 level up, so it doesn't touch this. contact. Yeah, and start filling in more bits, and then thinking about the next stage, and I have to connect this output to the input of the next stage, which is the clock input. And there's yet another wire going on this side of the relays. So I'm really getting cramped for space here. Then I stop at this design and I start anew. This time I flip this relay around 180 degrees. So instead of the coil being at the bottom, it's at the top. So it's here. This gives me my clock input a little bit higher. It's here, but this allows me to run my output a lot nicer, because now I have space for this resistor right here connected to the contacts instead of here. So it'll fit about there. So that allows me to put a joint after the resistor and just join it straight to the next clock input. So that's the biggest difference between these two. And then again, I start joining things together. I made a little bit of a mistake here. My capacitor sits there and my LED sits there. Yeah, so I keep puzzling until I'm not happy. Considered putting the capacitor on top, and I didn't like this idea. So yeah, I just keep on iterating. On this side I rotated the LED 45 degrees, which makes things easier. These two, they'll be running on top of each other. And I didn't like that. I thought, well, why not just, instead of this resistor lying flat, just have this line going straight and have the resistor going down into the page and then connecting through the LED at the bottom. So I immediately stopped that design and just skip on to the next one. And again, then I thought, well, it's gonna get tight here because I need to connect this side of the relay to the positive line. So I thought going up and across and down for each set, and I didn't like that. I'd much rather connect them through on a lower level on this side, connect them through that way, and then have them joined only at one point to the positive rail. So that's this design. Here you can see the positive is being pulled horizontally from one relay to another, and there's only one connection to the top going lower down. So I was quite happy with this layout. These Q points, they have to go to the next circuitry. There isn't really enough space between the relays, so I decided to put them here in between. Got more space there, so they were scrapped. Yeah, I double checked all my schematics. These little things, this angled things, means these wires are lying higher up. Same with this one and that one. Yeah, and then checking everything again and again. Here I came to the funny conclusion that I'm an idiot, because basically my clock signal is going into the left. Let's divide by 2, divide by 2, divide by 2. So this is actually my least significant digit, and on the right side is my most significant digit, which is wrong. It should be the other way around. Plus my clock input, the dial will be on the right side of this relay circuit. So yeah, I had to change the order around. You know, you could say just turn the circuit upside down. We got our least significant digit most and the clock inputs on the right side. But then my power lines are on the bottom. They should really be at the top. And also my outputs, they'll be at the top, and they'll have to float all the way across the circuit to the next relay logic circuit. Didn't want that. They should just jump from here to there. So okay, so I had to start over again. The top part pretty much stays the same. I just flip the bottom relays. So the diodes are going the other way, the LEDs flipped around. But still, this output can connect into the next stage just on the other side of the relay. So this is the final design, which I'm going to build. I also changed the outputs in the middle of the relays. Yeah, so this is my master plan. I've changed these 150 ohm resistors to 510. It's this resistor here. Originally it was 150 ohms. On the circuit they used only 100 ohms, and it's the closest value I had lying around. But I thought, well, it's still passing a lot of current when the capacitor is empty and it's being charged up. So I wanted to increase this resistance to reduce the current charged in the capacitor to avoid current spikes. So basically what I did, I built the circuit, left this resistor out, and I kept on going up in value with this resistor until the counter didn't work anymore, because the capacitor can't charge up enough or discharge enough while the clock input is low, logic high. So during the sampling time basically determines how big or how small you can make this resistor. And I found out that the circuit begins to fail between 780 and 710 ohms. So I knew I had to stay behind 710 because here funny stuff started happening. So again, I decided to go quite a bit lower to make sure that the circuit will definitely operate correctly. That's how I got the 510 ohms, because I have them lying around. That's why I chose the 510. I have plenty of those. And that gives me a charge current of about 24 milliamps, while with the 150 it was about 80 milliamps at 150 ohms. So that's a lot better. All right, so let's get on with it.